So in our last video, we talked about what is magma, what is lava, where would you find molten rock, what is the whole idea of magma plumes, which happens at hot spots, divergent boundaries, and subducting plates. We talked about how temperature above the melting point is necessary for you to melt rock, and that it usually happens between 800 and 900 degrees, but that depends on the pressure the rock is under, because more pressure makes the material more solid-like and therefore harder to melt. We also talked about the fact that mixtures make the material melt at different temperatures, and then adding fluids makes it easier for the material to melt. And then we talked that in order for rock to melt, the temperature has to beat the pressure. And so the two easiest ways to doing that, and we kind of explained that on these charts, is that remember that temperature is increasing as you go deeper into the ground, both underneath the continents and the oceans, a little faster under the oceans than under the continents. But the rock will typically not melt at the beginning of the first 150 kilometers, because in order for the rock to melt, you need to be a lot hotter than it is at that point. It will start melting though, becoming more liquid-like around that temperature, or around between 900 and 1500 degrees, but it won't melt completely until the second blue line. And we talked about the two easiest ways to make high rock melt is to either make it rise, so it's already hot and it doesn't lose a lot of this heat, and you make it rise but under the same kind of temperature. That means that it's going to be under less pressure and it's going to cross that melting point line. And remember that since in the mantle there's very little conduction taking place, that means that this can happen. The rock can rise without losing much of its temperature, and so you're going to make the rock melt under these conditions. And that's why hot rising magma plumes cause the surrounding rocks to melt as well. We also talked that if you wet the rock, you lower the onset of melting, and therefore you're going to make this rock easier to melt. Now, this all helps us understand the interplay between the layers of the earth and magma formation. If you look at the first layer of the earth, or the lithosphere, that's going to be, the temperature is very low, so that means the rock will tend to be solid, because even though the pressure is also low, which lowers the melting point, the rock is not going to be hot enough to melt. And so since the temperature is not high enough for the melting to occur, the rock is going to be solid, and in this case it's very brittle-like. All right. Now once you get to the asthenosphere, temperatures are increasing both underneath the continent and the ocean, a little faster under the ocean than under the continents. So the ocean is going to have to get to that melting point a little faster, unless of course you're talking about wet continental rock, which does happen along subducting plates. Remember that. So along subducting plates, because you met the rock, you lower the onset of melting, which makes the rock melt. This could also happen if something causes the rock to be uplifted to an area of lower pressure. Okay? But whenever you have this asthenosphere, the temperatures are getting high. And so you get to those first 100 kilometers with that magic line where the rock tends to melt. But the pressure is also a little high. So that's also increasing the melting point. So the melting point is almost reached. All right? And so the pressure is kind of almost waning, but not too much. And so what you end up like is a plastic-like rock that flows sideways due to the mantle convection underneath it, carrying the brittle pieces of the lithosphere, causing plate tectonics. Underneath that, you have the mesosphere. Now, on the mesosphere, or the lower mantle, notice that the line of melting is finally actually going to be reached. And so, right at the bottom of the melting, you're going to have actual melting taking place. Now, notice that at the upper mantle, you have that magic line right there. I forgot to actually point at the graph when I was talking about it. But notice that at the surface, it's going to be too cool, too brittle. Then you hit that magic point where this first 100 kilometers right there, when you have a possible melting, if you get uplift or wetting of the continental crust on those conditions. Then after that, even if you are plastic-like, it's not going to really melt, because the rock, the gradient of how the geothermal gradient is going to decrease, and the temperature is not increasing as fast because the materials are getting denser and denser. All right? But then as you get to the mesosphere, the pressure is so intense, the density is so high, that the rocks will definitely not melt, because the melting point is increased so high. You can see that, how the melting point line is moving to the right side. So you're not going to have a lot of melting taking place. Even though the temperature is high enough to make the rock try to melt, the pressure is so high that it increases the melting point so much that the rock will never melt. That's true until you get to the very bottom of the mesosphere. Okay, so on the mesosphere then you're going to have super dense rock, although remember that the super dense rock can still move in convection cells, and that's what's weird about it. The dense rock will still move around in convection cells, which are causing the rock to rise, and this will eventually push the asthenosphere higher, leading to that possible melting that we talked about on the top. Alright, so then you're going to get to the bottom of the mesosphere, where heating from the core, the outer core, is going to heat up that rock so much that you get to a transitional zone where some rock will start to be pushed beyond the onset of melting, and it's going to start melting because the temperature is so high that even though the pressure is really high, it's increasing the melting point, the temperature will be higher than that, and it's actually going to cause the rock to melt. And when you get to the actual magma, that line has been crossed, and the geothermal gradient is increasing more than the actual onset of melting, and the rock is actually becoming liquid on the outer core. And you have this flowing ocean of rock that's melted, causing the electromagnetic field of the earth and all of that. But remember, pressure is still increasing. And as the pressure is still increasing, the onset of melting is moving to the right, right? And eventually, when you head to the inner core, the pressure is so high that even though the temperature is extreme, you cannot melt. So the rock wants to melt, but it won't because the melting point is increased tremendously because of the massive amount of pressure, and the rock will not melt even though it's at high temperatures because the pressure will force the material to remain solid, and that's the iron and liquid crystallization that happens in the core. Alright? That explains to us the layers of the earth and why they are the way they are. And I hope you kind of get a general picture of what we're talking about. You can study these little drawings, review the layers of the earth, and kind of try to make sense about why the lithosphere, the asthenosphere, the mesosphere, the outer core, and the inner core are the way they are. It all has to do with how fast the temperature is changing, why is it changing slower, why is it changing faster. Remember, as the density increases, you're going to reduce the speed at how fast the temperature will actually increase. And the only reason why you have this rapid increase in temperature here is because of the lowering of the density as you hit the bottom of the mesosphere, because of the heat that's receiving because of the core, causing those magma plumes rising, which is lowering the density. And so you have 2 points of melting. You have the outer core, which is definitely melted because the rock is actually above the onset of melting, and you have melting possibly happening at the bottom of the mesosphere, and it might actually happen if you have uplift taking place, and you have the same scenario up here in the top of the asthenosphere, and that will happen if uplift takes place or if wetting of the continental crust takes place.